Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, minimum moves to spread stone over grid. The problem is very interesting, and in this video we'll be looking at one interesting follow-up to this problem as well, in which the grid size can be anywhere between m cross n less than equals to 21. So if you are here just to watch the follow-up, you can skip to that particular section. All the timestamps are there in the description down below. So with that, let's get started. The problem states that you are given a zero indexed matrix grid of size 3 cross 3 representing the number of stones in each cell. The grid contains exactly 9 stones and there can be multiple stones in a single cell. In one move, you can move a single stone from its current cell to any other cell if the two cells share a side, and you have to return the minimum number of moves in which you can move the stones such that each cell contains one stone, right? So let's take an example. Let's say this is the given grid. So here you can see the first cell contains one stone, second cell contains one stone, and so on and so forth. So notice that this cell contains two stones and this cell contains 0 stone. So we have to transfer one stone from this cell to this cell. Now you can't directly transfer from any cell to any cell. You have to follow this rule. Basically you can transfer to any cell which shares a side. So what you will say, okay, I will transfer one stone to this cell first. I will transfer one more stone, like now the configuration would be this will be 1, this will be 2. Now I will transfer one stone from this cell to this cell, right? So now this will be 1 and this will be 2. Now I will transfer one stone from this cell to this cell. So again this will be 1 and this will be 1 again. So in total you make 3 moves. In 3 moves you arrived at a configuration where each cell has exactly 1 stones, right? So in you can try any other possible combination and you will see you will not be able to reach the final configuration, that is 1 stone per cell, in less than 3 moves, and hence the answer here is 3, right? So hope the problem statement is clear. Now how to solve this? So let's say this is the grid, right? And we have to move cells. So we have 3 zeros here, right? So we know that we have to move some cells here, we have to move some stones here. Now it is given that the grid contains exactly 9 stones. So we are very sure that the final configuration will be something like this. Every cell will contain 1 stone because there are 9 cells and the grid contains exactly 9 stones. So every cell at the end will be containing exactly 1 stones, right? Now once we know that this is the final configuration, we know that we will be transferring 1 stone from here, and we also know that we will be transferring 2 stones from here, right? So let's and we know that one of these 2 stones will land in one of these 3 cells, and similarly one of the stone that will be transferred from here will land in one of these 3 cells, right? So in a sense what we have is we have 3 cells which are deficient of stones. So we have these 3 cells which actually need stones, and we have 3 stones which are extra. So 1 stone from 2 comma 1 and then 2 stones from 2 comma 2, right? Now the problem is we have to just make sure which cell will receive which stone. So you can say, okay, this stone will be received by this cell, this stone will be received by this cell, and this stone will be received by this cell, and there are other possible combinations as well. So let's assume that you reached a configuration. Let's say you assume you say that, okay, I know that 0 comma 0 will receive the stone from 2 comma 1, 0 comma 1 will receive the stone from 2 comma 2, and 0 comma 2 receive the stone from 2 comma 2, right? Now once you arrive this configuration, how will you figure out the number of moves required? Because finally you need to return the number of moves, right? You don't have to return which stone goes to which cell. So we are saying, let's take this first case where 0 comma 0 receives the stone from 2 comma 1. So this is 2 comma 1 and this is 0 comma 0. So we are saying this stone will be transferred to this cell. Now there are various possible ways. You can either go this way, right, all the way to here. You can also go this way all the way to here, or you can go this way, or you can go this way as well. So there are various possible ways. Now if you know that you will be transferring one stone from here to here, you will try to find out the way in which you will require minimum number of moves, right? And what is that way? That way would simply be go all the way up to this particular row and then go all the way to the left or right based on where your target cell exists and reach the final target column, right? So what you are saying is, we to reach from here to here, you at least have to travel these many rows for sure, and to reach from this cell from this column to this column, you have to travel this much column for sure. So what we are saying is, the minimum number of moves will be the one where we will just traverse the difference between the columns and the rows, right? So in this case, the difference between the column between the rows is 2 minus 0, which is 2, and difference between the column is 1 minus 0, which is 1. So in total we will be requiring 3 moves, or minimum 3 moves, to transfer the stone from 2 comma 1 to 0 comma 0, or vice versa. And in the same fashion you can calculate for this as well. This will also require 3 moves, and in the same fashion you can calculate for this as well. This will require 2 moves, or minimum 2 moves, to transfer the stone from either 2 comma 2 to 0 comma 2, or vice versa as well, right? Now you notice that here we require 8 moves to actually achieve this particular configuration. Now we just have tried one possible arrangement. There are many arrangements, right? So we have to try them all. This can be one possible solution. So what you will say, okay, I know what all cell are deficit of stones, and I know which all cells from where I can transfer the stone. So I will arrange all these cells in all possible manner, and I will try the combination with each of the configuration. So I will say, okay, 0 comma this cell will receive the stone from this cell will receive the stone from this, and this cell will receive the stone from this. And I will try another configuration in which 0 comma 0 is receiving the stone from the cell 2 comma 2, 0 comma 1 is receiving the stone from cell 2 comma 1, and so on and so forth. So I will try every possible configuration, and whichever gives me the minimum number of moves, that will be my answer, right? So what will be the, first of all, about correctness, this is correct. Why? Because we are trying out every possible configuration. We are sure that this will be the final configuration, so we are actually sure about what cell will receive the stones and what cell will, from which we will transfer the stone from. So we can, what we are saying is, we will try all possible configuration of this donor to the receiver, and we will pick the one which will give us the minimum number of moves. So this problem is trying out all possible configuration, and hence it will give us the correct answer. Now what will be the time complexity? The time complexity would be, notice we are arranging the donor side in all possible configuration. So let's say there are total d number of cells from which we will be giving the stones to the cells which are deficit of stones. So in total, in worst case, there can be d factorial number of combination. Why worst case? Because there can be duplicates as well, and in the case of duplicates, the combination we have to divide it by the duplicates values, right? d1 factorial, d2 factorial, and so on. So we will not go there. Basically, in worst case, there can be d factorial number of choices that you might have, right? Now what will be the value of d here? The value of d would be, in worst case, 8. Why 8? Because notice how many, this d is actually equals to how many cells are there which are deficit of stones, right? So number of cells which are deficit of stones is equals to number of cells which have extra stones, because we have exactly 9 stones, right? So this d will be equals to this, the length of this array. And in worst case, what can happen is only one cell has all the stones and all other cells are empty, right? So the worst case value of d is 8. So what we have is 8 factorial is the number of combination. Now notice this is not completely true, because in case only one cell has all the stones, you just have to divide by d factorial as well. So that will not go there, but in worst case this can be the possible configuration, right, overall. And for each configuration, what we are doing is we are iterating over this entire array and then figuring out the number of moves required. So for a single cell, we just subtract the rows and the columns to get the number of moves required. So we'll do this for all the cells. So in total we are doing d operation for each configuration. So in total we are doing d operation for this 8 factorial configuration, and this entire thing is well within the time constraint of 1 second. So you will be able to code this entire thing up. Basically you will try all possible configuration and then figure out the one which will give you the best result. So the problem is now straightforward. The solution is we'll just try out all possible configuration and see which one is giving us the minimum moves, and that will be our answer. So what you need to code? You need to code a way to give, which will give you all possible permutation of this particular array, and with each permutation you already know how to find the number of moves. So either you can use the built-in permutation function of C++, or you can find the permutation yourself by using recursion, right? So I will not show you the code, pseudo code for this. Next we'll be looking at the code, but I would strongly encourage you to code this entire thing by yourself before moving ahead, and then we'll look at the follow-up problem as well. So the code is straightforward. We have built this zero array and non-zero array, which basically this zero array are the cells which have 0 number of stones, and non-zero array will contain the cells which can donate the number of which can donate some stones to the other cells. So basically this will be the non-zero array which can have repeated elements, and this will be the zero array, right? Now we simply see if grid has non-zero value, we will insert this particular cell j comma k these many number of times, right? And if it has zero value, then we will simply insert the cell in the zero array. Now once we build this zero and non-zero array, the next thing is to actually find the permutation of non-zero array, and then we will find the number of moves required for that particular permutation. So for that we written a arrange function which takes in this taken function, which is a boolean array, which will denote whether we have taken some element already or not in the previous iterations, and this order denotes the actual permutation order. So what we have done, we will simply see if for each turn we will see what if something is taken, we will not consider that. If something is not taken, we will try to take that, right? So we are taking this particular element I, so we mark this element as taken, and we also push the element in the order array. Basically the next element that will be there in the permutation will be the ith one. Now finally we call the function arrange again. So basically this will make sure that we are not taking a single index twice, right? Now once we have figured out once we have done with the permutation where I am taking the ith element in the current iteration, I will simply remove the ith element from the current iteration, and I will try other elements in the current iteration. So basically what we are saying is we have a boolean array of size 3, and in every iteration I will make one of these 0 as 1, and that will be the element that I am taking. So in first iteration, what will happen is, let's say these are the 3 elements. So in first iteration, I will iterate over this. I will pick one of them. So I will first pick 0, let's say. Now if I pick 0, this will become 1, right? So in the second iteration, I will not pick this one. Instead, I will pick one of these 2. So let's say you pick 1 here, so you will make this one. In third iteration, you will pick, let's say there's only one choice, so you will pick that. So this is the one possible configuration. Now you recurse back and say, okay, now after 0, I will not pick 1, instead I will pick 2. So now this is the next in the order, and after that you will pick 1. So in this fashion you will continue, and you will finally explore all possible permutation. So that's where we have just reset our taken and order array, so that we can recurse back. When we recurse back, we know which all things are not actually taken, and we can take those as well. Now finally, once we have the permutation of all the n elements, we will simply go over the permutation. So this is the order j is the element at the current index. So if 0 to 1, so 2 is the second element of this array, will map to the first element of this array, right? So that's what we have done. We know that non-zero of order of j will map with 0 of j. So we simply find the distance and add the distance of each cell, and finally take the minimum across all of them, right? So this will be the distance function. Basically we'll just do the difference between the rows and the columns, right? So this particular solution will pass, and the complexity, as we have already discussed, is d factorial into d. Next, let's look at the follow-up problem wherein m cross n is less than equals to 21. So in other words, here you can't actually apply the same algorithm, because the previous algorithm was d factorial, where d is the number of empty cell or number of cells with extra stones. In this case, d factorial would be 21 factorial in worst case, right? Again, not exactly 21 factorial, but we can assume it to be 21 factorial, and this will not pass. The previous problem, the constraint was the grid size cannot be greater than 9, or is exactly 9, so that's where 8 factorial was passing. But here 20 factorial or 21 factorial will not pass. So we need to do something better, right? Now how to solve this problem? So if you haven't think about this problem yet, I would encourage you to pause and try to at least give it a moment and try solving it. So hope you thought about it. Now we will use the exact same technique. The only thing we will do different is, notice that here we are trying to find out all permutations. So we find out these 3 permutations, and then we actually find the number of moves required by comparing it with the given 0 array. But do we actually need these permutations in themselves? The answer is no. We only care about the number of moves required, right? So we don't care about whether the permutation was 0 1 2 or 0 2 1 or anything else. We only care about number of moves required. So if we only care about number of moves required, whenever we say that okay, the first element will be mapped with 0, I can simply find the number of moves required from here and be done with it. I will not need to store that 0 was the first element that I picked, right? I can just simply say that 0 is used, and that's it. Because I already taken the score, I don't need that information that 0 is the first element. Now because the actual order in which we have taken the element is something we don't need to actually store till the end, we can optimize. Now how? So notice that this was the algorithm previously, wherein we were trying to find out if something is taken, we will not take this array, and then if it is not taken, I will try to take it, and I will arrange the remaining possible numbers, and then I will simply mark it as untick so that I will try another possible configuration, right? So in each, if there are, let's say, four spaces, in each arrangement I am trying to fill one space at a time. So I will see, okay, if I put 0 here, then give me the number of ways in which, give me the number of moves required to, a minimum number of moves in which I can fill remaining 1, 2 and 3 in this remaining 3 spaces, right? I don't need the information that give me exactly what all are the configuration. So if you need what all are the configuration, you don't have other choice. You have to actually list all the 6 choices. So all the 6 choices would be 1 2 3 1 3 2 2 1 3 2 3 1 and finally 3 2 1 and 3 1 2. So if you ask for, okay, list me, give me all the permutation, after you have fixed the current one, you have to list all the 6 choices here. So you can't avoid iterating over a array of size 6, right? But now we are saying that, okay, I don't need permutation, I just need what is the number of moves that mere number of moves that I can get by arranging these 3 elements 1 2 and 3 in the remaining 3 spaces. So with that, instead of getting this 6 sized array, what you will be getting is a single number x, and that is sufficient for the current problem. So hope you got the intuition why an optimization is possible here, right? Now because we don't need actual order, we can simply replace this order, and while taking an element I can simply find out the distance at this stage itself, right? So the pseudocode would be transferred to something like this. So if you see, this is exactly similar. Only thing that we have done differently is, instead of actually maintaining an order array, we are not maintaining this order array. Instead, whenever we say, okay, I have taken the ith element in the current position, so there are, let's say, again there are some position and we are, let's say, filling this particular position. So I have said that, okay, I have taken ith element for this position. So what I will do, I will simply find the distance between the ith element and the 0th element of the 0 array. So this is the distance I will find out. 0th element of the the 0th element or the current number. Let's say I am filling up the index c in the current iteration. So I will just pick the cth element of the 0 array and map it with the ith element of the non-zero array, right? Now once we have figured out the number of once we have mapped this particular element and figure out the distance, I will simply say, okay, now give me the number of minimum number of moves required to arrange the rest of the elements, right? And this way we actually don't need to store the order array, right? Now look at this, there are lot of duplicate processing that are happening here. Why? Let's look at an example. Let's say this is one possible configuration of size 3 cross 4 where we know that this will be the final answer. So we prepared the 0 array and the non-zero array, right? Now let's say you have filled 3 elements. So you, in the first iteration you picked this element, in second iteration you picked this element, and in third iteration you picked this element. So we have reached this particular iteration. What this means, it means that, okay, I have taken the second, fourth and sixth element. Now give me the minimum number of moves in which I can arrange the remaining elements in the remaining moves. So basically what we have done is we have mapped this thing to this, right? We have mapped this to this, and then we have mapped this one to this. Now we are left with these 3 elements, right? And we are left with we have to map this with these 3 elements. So what we will say, okay, I know that this is the configuration. Now give me the minimum number of moves in which I can arrange these 3 elements with these 3 elements, right? Now you will get a number from here, let's say x, right? Now let's think about this configuration in which we are taking this as the first number. So in other words, the mapping now is this is mapped to this, right? And this is the second number. So this one is mapped to this, right? And this is the third number, which is this one is mapped to this. Now again we will be saying give me the number of ways in which I can arrange the remaining 3 elements with the remaining 3 elements here. So you will be getting the exact same x here, right? So you see, with different configuration we can arrive at the same sub problem. So if we have seen this, I hope you understand that we can simply memorize this particular solution to actually avoid recomputation of the same state again and again, because same state will come eventually. So what will be the overall time complexity now? The overall time complexity would be, we will simply try out, like we will simply use this function and memorize this function, and that will give us the final result. Now what this function is taking, let's say okay, first figure out, let's say we first figure out what is the time complexity for a single iteration. So for a single value of taken, what is the time complexity? So what we are doing inside this, we are simply iterating over a zero size, with iterating over the array of size of 0, and we are doing some operations here. These all operations are constant time operations, right? Now this entire thing will run in order d time, assuming that size of the array of 0 is d. Now how many different ways are there in which this arrange can be called? Now why I am talking about different ways, because we will be memorizing this. So for a single way we will be executing this entire function a single time. So number of different ways would be 2 power d. Why? Because this is just a boolean array with 1 or 0. So this taken would just denotes whether a particular index is taken or not. So in total there can be 2 power d possible configuration of this array. So this arrange function can be called 2 power d times. So 2 power d into d is the overall time complexity of this entire function. So this should pass for 21, but Leetcode is famous for the tight time constraint as well. So but it will pass for 18 for sure. So basically we have reduced, the thing to take away here is we have reduced the complexity of the solution from n factorial to 2 power d. So exponent from factorial to exponentiation, which is a lot better, right? So hope this entire solution makes sense. I would strongly encourage you to code this entire thing by yourself again before looking at the code. So next we will be looking at the code. The code is again very straightforward with what we have discussed. We simply build this same array, and 0 and non-zero again, and we find out the number of moves. So for this number of moves we simply say, okay, if we have actually iterated over, or if we have tried out all possible configuration, or if we have matched everything, so in that case this mask will contain 1 power n or 2 power n minus 1, right? So basically this, instead of storing this boolean array, I am just converting this boolean array to a simple integer. So let's say this is the boolean array. So instead of storing this boolean array, I am converting this entire thing into its decimal format. So if you see the decimal format, this will be 248, this will be 17. So I will say 17 will contain the state for this particular array, right? So we have discussed this bit masking technique a lot of time in this channel. I will link some of the videos in the description below, you can check that out. So we simply we simply checked what is the if the entire thing is filled, if the entire thing is already matched, we'll simply return 0. Otherwise we looked at the cache. If it is already computed, we'll simply return that particular answer. If it is not computed, then we'll compute it. Now which index we are currently filling, it actually is equals to number of things which we have already filled. So if we have let's say already filled 3 indexes, so I am actually now filling, or I am actually now finding the match for the fourth element of this particular 0 array. So that's what we have done. We simply find out the number of bits, and after that we checked the which one is giving us the best distance. So we tried to map every I with the current index position and find out the distance, and based on that we figure out what is the number of moves required for the remaining things to match up, right? So this entire thing, as discussed, will learn in 2 power n into n time, where n is the number of n is the size of the 0 array, which in worst case can be m into n as well. So hope this entire solution makes sense. If you have any doubts in this particular problem, feel free to post them in the comment section below. I would be happy to answer. And with that, I will see you in the next one. Thank you.